Political Science Center. Okay, and then we are happy to present you Professor Jan Soibelman of Kansas State University. Professor Soibelman is a distinguished university professor at Kansas State University. Professor Soibelman has done important works in many areas of mathematics, such as quantum groups, mirror symmetry, homological algebra, representation theory, Donaldson-Thomas invariance, etc. In the long collaboration with Professor Maxim Kontsevich, he proved the famous Deline's conjecture in 1998 and proposed relation of mirror symmetry and non-Euclidean geometry and tropical geometry in the year 2000, and discovered new type of wall crossing formula in Donaldson-Thomas theory and gauge theory in 2008. He is distinguished. He holds a distinguished visiting research chair at the Perimeter Institute. So, without further ado, it's my pleasure to invite Professor Soibelman to deliver his talk on holomorphic Floer theory and exponential integrals. Okay, please.
Thank you very much. Thank you for the invitation. Actually, it's my second colloquium talk at the ER Mathematical Science Center, but first one was in person, I believe, like 7 years ago. And it was another joint project with Kontsevich, which I was talking about at that time. Let me see whether I will be able to move. No, I can do it manually, but it's okay. All right. Let me start with a long motivation. So it's a colloquium talk, and it's sort of a prerequisites. I decided to choose a Morse theory, which probably the topic which somehow familiar to everyone. The Morse theory is in this simplest form. It starts with a compact real smooth manifold and the smooth function on it, which is supposed to be a generic function. More technically, it's Morse-Smale. It's all finitely many critical points are isolated and non-degenerate. All right, with this data and an auxiliary choice of a generic Riemannian metric, one can associate a cochain complex, which is a Morse complex, in which computes a cohomology of X. So if we work over, say, complex numbers, although everything can be done over integers, but let's work over complex number, then as a graded vector space, Morse complex is generated by critical points of the function f. And each critical point generates one-dimensional vector space, which we place in degree minus index of this critical point. Index is a number of negatives in the Hessian matrix, in the Hessian quadratic form. So this is a graded vector space, and it carries a differential. So the differential, d Morse, can be written explicitly if we use this Riemannian metric. So we consider all critical points with the index, which is index x plus 1, and the differential applied to the generator is just an integer linear combination of such points. And the most important part is this number, nxy, integer number. It's a number of gradient lines, which starts at x and ends at y, and with my conventions, I believe I should take gradient lines for the function minus f. All right, so anyway, there is some cohomological complex, and its cohomology is isomorphic to any other cohomology of X computed, for example, using the de Rham complex of de Rham differential forms. And the main thing is that this theory is, if you're a physicist, you would say that this theory is topological. It does not depend on the Riemannian metric. And it also does not depend on the Morse function if it belongs to this class. So then one can say that starting with a pair, compact smooth manifold and the Morse-Smale function in it, we assign to it a cohomological invariant, which is this complex, MXF, and this invariant does not depend on F. So all choices are equivalent, which means all complexes are quasi-isomorphic. So they compute the same cohomology. All right, so the same story can be spelled out in a different language, in the language of Floer theory. So we start with a symplectic manifold, cotangent bundle to X. It's a real symplectic manifold. And consider two Lagrangian submanifolds, a zero section X and the graph of the differential of the function. Then with this pair of Lagrangians, one can associate a complex called Floer complex of this pair, and it is defined, as you can see, in a very much similar way. It's a direct sum of intersection points of L0 and L1, but these intersection points are exactly zeros of the differential, so they're critical points of F. And there is a natural grading. So the story is more general than this particular choice of two Lagrangians. So in general, these critical points are graded by the Maslov index, which in this particular case coincides with the Morse index on the previous slide. So there is a Floer differential. That's the main discovery of Floer. On this graded vector space, there is a cochain differential of degree +1, square equal to 0. And it is defined, in a sense, it's similar to the Morse differential. It's a direct sum. It's a sum, but of what? One consider, so this is a picture which explains what is it. It's a sum of pseudo-holomorphic disks with the boundary on these two given Lagrangians, which means that you take a standard holomorphic disk and mark 2 points on its boundary, P0 and P1, and you consider maps from this disk to your symplectic manifold, which is a cotangent bundle here. The condition is that the upper arc maps to L0 and the lower arc maps to L1. So these 2 points go to the intersections, L0 and L1, and the restriction on phi is that it's pseudo-holomorphic. A cotangent bundle does not have a natural complex structure, but it has plenty of almost complex structures which are compatible with this symplectic one. And so you choose a generic and you speak about holomorphicity in terms of this almost complex structure. It doesn't have to be integrable. All right, so anyway, you define the cochain differential. So you have a cochain complex, which is, by the way, quasi-isomorphic to the Morse complex in this example, and it also doesn't depend on the choices. So this is the real story, which real means C infinity. And so approaching to the main topic of my talk, I will ask myself and the audience, I will ask the question in the spirit of Vladimir Arnold, what is a holomorphic or complex analog of this story? You know, Arnold often asked question, what is a complex analog of something? What is a complex analog of the real boundary, for example? And so what's the complex analog of the Morse theory? And he answered that question in a sense, he answered himself. It's a Picard-Lefschetz theory. And his point was that if you are in the real category, in the category of C-infinity manifold, so then you have to cross the critical level of the function, and this is what happened in the Morse theory. But when your function is holomorphic, then you walk around its critical fiber, its level set of the function of the critical value. And so then his answer was that the complex analog of the Morse theory is Picard-Lefschetz theory. What I'm going to talk about is another, in a sense, related structure, but which admits a generalization far beyond Picard-Lefschetz theory. And this is sort of one of the main structures for my talk. In my talk, we call it with Kontsevich wall-crossing structure. So the definition will appear much later, but taking it as a black box, let me explain how it appears in this holomorphic framework. So this means that we start now with a complex manifold, X, say complex dimension N, and a holomorphic function on X, which has finitely many isolated Morse critical points, and all critical values are different. So these are critical points, these are critical values of the function on these critical points. So since there is a holomorphic function on X with which is Morse, X is automatically non-compact. Otherwise, all functions would be constant. And so just for simplicity, let's assume that X is an affine algebraic variety, smooth affine algebraic variety, and F is a regular function, which means that at infinity it has sort of a polynomial growth. Otherwise, we should, if we take more general holomorphic function, we should impose some restrictions on its growth at infinity. All right. But now, if you want to construct a Morse complex, for example, for the real value of this function, it's also a Morse function on this manifold, we see that all critical points have the same Morse index equal to the dimension of the manifold. And therefore, there are no gradient lines because they join critical points with index which differs by 1. So the Morse differential is trivial. And similarly, let's consider in the cotangent bundle to X, let's consider the same to Lagrangian submanifold, zero section and graph of the differential. But now everything is holomorphic. T star of X is complex manifold. This is a complex Lagrangian, and this is a complex Lagrangian. Of course, we can consider them as just C-infinity. C-infinity symplectic, C-infinity Lagrangian, C-infinity Lagrangian. That's fine. But then, generically, there will be no pseudo-holomorphic disks with the boundary on the union L0 and L1. And therefore, the Floer differential is trivial. So, well, from some perspective, it is good because there is no differential. It's easy to read cohomology, but something is missing. And in order to see what is missing, in order to uncover this structure which is specific for a complex category, for the category of complex manifolds and holomorphic functions, let's consider a one-parameter family. f divided by h, where h, well, of course, it's suggestively called Planck constant, but so far it's just a complex, non-zero complex number. Then, if we consider the real value of this holomorphic function, it's a real valued function, and so for some values of h bar, there will be gradient lines joining critical points. This happens when this complex number belongs to a certain array, which I called Stokes array. So, and similarly, it's exactly parallel story for the Floer theory. If we take here, if we take a graph of differential of f divided by h bar, then for the same Stokes rays, we will see pseudo-holomorphic disks with the boundary on the union of two Lagrangians. So, so then the differentials will be non-trivial. And so we will have a non-zero, in fact, integer number of gradient lines, or these pseudo-holomorphic disks, which I call Stokes indices. And they can be organized into certain isomorphisms of the cohomology of the Morse complex. We can take h bar, say, below the Stokes array on the right-hand side of the Stokes rays and on the left-hand side. So there will be two cohomology groups, two vector spaces, and these Stokes indices can be organized as isomorphism between these two vector spaces. So I call them Stokes isomorphism. So one Stokes isomorphism for each Stokes array. And it turns out, so that's in a sense a key observation, that these Stokes isomorphisms are equivalent to certain relations between these numbers of gradient lines on different sizes of the Stokes arrays. This relationship between Stokes indices are called crossing formulas, and these are part of a much bigger story. I would say the whole theory of wall crossing formulas, which were developed by Kontsevich and myself in these three papers. I give archive references because it's easy to download them, to find them. And the mathematical structure which underlies wall crossing formulas in many, many examples. Some of them I will mention today, some others can be found in these papers. So the underlying mathematical structure is the wall crossing structure. And this is the structure which I'm going to discuss today in many examples, in several, at least in several examples, and kind of and axiomatically as well. All right, and again, a few points, maybe a few words about the introduction and also about part of the title, which I call Holomorphic Floer Theory. Let's look at the... yeah, okay, go ahead.
Sorry to interrupt. There was a question in
go
the chat
ahead.
about if the number of Stokes rays are finite.
Yeah, that's a good question. Not necessarily. And this is the main thing which confused people when they read our papers. No, it's always no more than countable. But in my today's talk, in most of my today's talk, there will be finitely many Stokes rays. But in more general, for example, in the theory of Donaldson-Thomas invariants, like in relation to representations of quivers and say integrable system and many other stories, when wall crossing structures appear, there can be infinitely many Stokes rays. Moreover, if I have time, which I doubt, to speak about Chern-Simons theory, there will be countably many. Stokes rays in Chern-Simons theory. Yeah, but kind of this is an introduction and motivation. So let's just think that always we have finitely many of them. All right. So let's consider not the Morse complex, but let's consider the de Rham complex. What does it mean that instead of just considering the manifold itself, X, I consider also a function on it, a Morse function. So this means that instead of considering the de Rham complex, omega of x with the de Rham differential d, I consider a twisted de Rham complex. And if I would like to incorporate this parameter h bar, so this twisted de Rham differential will depend on this parameter as well. So then I have a de Rham complex endowed with a family of twisted de Rham differentials. This story in physics, well, actually in mathematics, I believe too, it goes back to the famous paper of Ed Witten, supersymmetry and Morse theory, when he explained in the real and C-infinity settings how to derive Morse inequalities by deforming the Morse differential. But I will use this in the pure holomorphic framework. So, so my X is affine, so I can work with a global de Rham complex, but if it's not affine, I can do the same thing locally. So anyway, I have the algebra of differential forms with a twisted de Rham differential. So if I look for the cohomology as a vector space depending on H bar, then it will be an algebraic vector bundle over C star, which is endowed with a monomorphic flat connection. And so what we discussed on the previous slide in the framework of Morse theory or Floer theory, it can be spelled out in the language of differential equations, and the terminology matches, which means that if I look for the Stokes rays and Stokes isomorphisms for this meromorphic flat connection, it will be exactly what I discussed on the previous slide in the pure geometric framework. So this is suggestive, and this also suggests that if we are in the holomorphic framework, then there is not only the Morse theoretical, or I would call it Betty side of the story, or Betty, Morse or Floer. I call either of them the Betty side, because it's sort of topological. There is also the de Rham side, which is algebra geometric.
Yeah. The D module is on X or on
D module on C star.
Okay, thank you. Yes.
Yeah. All right. So what I'm saying that in the C-infinity framework, we had only Morse theory, which means we had only Betty side. But if we pretend to be algebraic geometers, we have also de Rham side, and there should be interplay between de Rham and Betty side. And indeed, cohomology computed on the de Rham side, yeah, are isomorphic to the cohomology computed on the Betty side. This is true in C-infinity case as well, but in the holomorphic framework, it's a part of the Riemann-Hilbert correspondence in this particular case. And more generally, when we consider more general complex symplectic manifolds and more general Lagrangian submanifolds, it's a part of our generalized Riemann-Hilbert correspondence. Our means Maxim and myself, and it's a part of holomorphic Floer theory. So holomorphic Floer theory, which I don't have time to talk about in kind of with any precision. So it's a project which is devoted to various aspects of the Floer theory, but in the framework of complex symplectic manifolds. As you have seen, there is some specifics, like, for example, this appearance of the parameter h bar and related vector bundles and d modules and so on. So in fact, it's kind of what I will be telling today is a corollary of certain categorical framework, which I'm not going to speak today, but just for you to know, in order to understand kind of the meaning, the essence of the results and formulas which you will see today, you should really work with categories, and you should replace Floer complex, which deals just with a pair of Lagrangian manifolds. You should replace it by a Fukaya category, which means that you should consider all Lagrangian submanifolds, all real Lagrangian submanifolds in the complex manifold, and so they can be, they form certain categorical structure, which is known as A infinity category structure. And this picture just tells you how collection of Lagrangians can interact. It's very much similar to the definition of the Floer differential, but now we count the pseudo-holomorphic maps of disks with a number of marked points on the boundary, such that each piece, each arc belongs to the corresponding Lagrangian. So then marked points go to the intersection points. And so altogether, this gives this infinity structure, which I will not use today, but I would like to mention it. What I will use today and what will be the main geometric objects, it's a complex symplectic manifold. Mostly it will be cotangent bundle with a standard symplectic structure, but not necessarily. And a pair of complex Lagrangian submanifolds. Mostly it will be zero section and the graph of the holomorphic function on the graph of the closed one form. And there will be, well, I would say 1.5 algebraic structures, because one I will discuss well, in some detail, and the other one I will discuss just in one example. So the wall crossing structure, which I have already mentioned, it's a main structure for today, but there will be one more structure, which is a quantum wave function structure, and in this particular, in my story for today, there will be some quantum wave functions associated with these two complex Lagrangians. Since I don't know how much, well, certainly I will not have time to speak about all my slides. It will be easier for me just to email them in the end of my talk, no matter how many of them I will explain, but I will start with examples of geometry of these pairs of complex Lagrangians and corresponding symplectic manifolds, which will be relevant for my talk. So there will be, I believe, 5 examples on the few slides. So, and I'll try to explain problems in which this geometry appears naturally. Main example for today, it's finite dimensional exponential integrals. So this is, what is it? F the same, actually F doesn't have to be Morse. Here it just any holomorphic, or if X is algebraic, affine, so it's a regular function. I choose some holomorphic volume form, top degree form. It can have 0, so X doesn't have to be Calabi-Yau. And I choose an appropriate class of integration chains. So it's a real and dimensional if n is complex and dimensional. So it has a real and dimensional cycle. And this is clear what is it. It's a top degree n form, exponential form, and I integrate it over the cycle. I will be interested in algebraic and analytic properties with respect to h bar of this integral, and underlying geometry is the one which already appeared. Symplectic manifold is a cotangent bundle, 0 section, and the graph of differential of f, if you'd like, differential of f divided by h bar. These are two Lagrangian. So the same story, but f is multi-valued, which means that instead of a pair x and exact one form, which means differential of f, I have x and the holomorphic closed one form. Then the geometry is very much similar. Holomorphic symplectic manifold is a cotangent bundle. One complex Lagrangian is 0 section, and another one is a graph of this one form. So these are two main examples, but let's consider something more interesting, especially if I will not be able to speak about the Chern-Simons theory. And I will be talking mostly, if I will, about complexified Chern-Simons theory. But so as a data, I start with, say, compact-oriented three-dimensional manifold. I fix the integer, the level of the theory, and the gauge group is a compactly group. GC, and G its complexification. For the most purposes of my talk, you may assume that GC is SU2 and G is SL2C. It's already very interesting. Now, fixing a knot or a link inside of M3, we can present M3 in terms of the surgery. Like, for example, we can consider we can consider a small tubular neighborhood of K and the complement of this tubular neighborhood. Then we can consider a symplectic, well, we can make it into infinite dimensional symplectic manifold, or if you are not afraid of stacks, we can make it into symplectic stack of G connections on the boundary of the tubular neighborhood of K. So, like, you can think of, if you consider them up to an isomorphism, just representations of the fundamental group of the boundary, which is the torus, so it's a very simple object. But anyway, inside of this symplectic stack, it carries a natural symplectic structure, and it's in fact complex symplectic manifold if we get rid of some singular, if we throw away some singular locus. Inside of it, we have two Lagrangian technically subvarieties if we do not throw away singularities, or submanifolds if we do. One consists of connections which can be extended inside of this tubular neighborhood, this handle body, and the other which can be extended outside. So the intersection consists just of flat connections on my three manifold, flat G connections on the three manifolds, and it is the same as the set of critical points of a multi-valued complex function, Chern-Simons functional, which is written here. A is a notation for the connection, for the G connection, and trace is just a killing form. So then, technically speaking, we have a holomorphic one form. But if you go to the universal covering, you can think that you have a holomorphic function. All right, this is something which mathematicians can understand, and this is something which mathematicians might have trouble giving a specific meaning. This is a partition function for the Chern-Simons theory. It's an integral over the space of all connections of this exponent of this section. It can, nevertheless, this expression can be given mathematical meaning in different ways. Kind of the most straightforward way is to consider perturbative expansion as k goes to infinity, sort of a stationary phase approximation, if you like, and present the answer as a sum of certain local inputs of the critical points, which are flat connections. A much less trivial way proposed long ago, now classical by Witten, Reshetikhin, and Turaev, is to use quantum groups at roots of unity. And here we need to have k to be integer. It doesn't matter for perturbative expansion, but it's important for quantum group story. And so we will interpret this partition function in a completely different way. Now, we can, so what I would like to say that we have two Lagrangian, complex Lagrangians inside of the symplectic manifold. Maybe not quite a manifold, but nevertheless, it's the same geometry as before. Now, if we consider a complement to the knots, I take this hyperbolic manifold and decompose it into the union of ideal tetrahedra. Then there is another way to give a partition function for this, if you like, three-dimensional manifold with the boundary, using some results of Fukaya. The answer will be given in terms of the Faddeev's quantum dilogarithm, which I don't have time to recall, as well as the details about this statement. So that's a paper by Dimofte and other people, which you can kind of look many more details and explanations. But so the puzzle arises why in the Chern-Simons theory one see Faddeev's quantum dilogarithm. And there is a, I would say, non-trivial answer to this question, and this answer, which I will briefly discuss later, it is related to the following geometry. I consider a symplectic manifold, which is a symplectic torus, C star in the power 2n, endowed with this holomorphic symplectic form. And inside, I consider two complex Lagrangian submanifolds, subvarieties. They are given quite explicitly. Well, for n equal 1, an example of what is written here is just a pair of pens, a curve in C star square. And L0 is a product of such things. The second one is essentially the coordinate torus. So I have two Lagrangians. One is a sort of a higher dimensional pair of pens, and another one is a coordinate torus. But to be pedantic, coordinate torus depend on the choice of some integer linear subspace in Zn. And so this integer subspace depends on the choice of the integer symmetric matrix. It's given by this equation. And so then the corresponding coordinate torus in this symplectic manifold, it's n-dimensional. It's what we are interested in. For n equal 1, when we have C star square, and C star square is not a cotangent bundle, so it's some new example of symplectic manifold for today. So we have a pair of pens, and with some choice of this integer matrix, the coordinate torus will be just C star, given, for example, by the equation, one of the coordinates is fixed. All right, so this example also is relevant to the Chern-Simons theory, although it's not clear how. Now, if we want to consider arbitrary Lagrangian submanifolds, and if you would like to ask, is there a natural problem in mathematics or physics whether they appear? For example, if these are, say, non-compact Lagrangian submanifold in the standard symplectic vector space, C to n, yeah, the answer is yes. We should consider a Feynman path integral with the boundary conditions on these two complex Lagrangian submanifolds. So this is, again, it's ill-defined. And so the natural question for mathematicians is to give a meaning of this symbol. It can be done perturbatively, but there is an alternative way to give a meaning to it, and that's something which is related to our theory of quantum wave functions. So as an action, we take this actually pretty standard action in the first order formalism. Yeah, and so the question can be asked, is there any relation between this Chern-Simons example C, between this strange pair of holomorphic Lagrangian submanifolds in the example D, and this path integral, which is quite general, in the example E? And the answer is yes, at least conjecturally. So what do we expect? That if you look at the perturbative expansion of this path integral, and it's pure formal thing using Feynman rules, and if you take as a boundary condition L0, L1, these two, this L0 and this L1, then what we get is a perturbative expansion of the Chern-Simons partition function as k goes to infinity, as long as this Planck constant h bar and k are related in this way. So then as k goes to infinity, h bar goes to 0, and so these two expansions should agree. There are some reasons why, but I don't have time to discuss it now. There is another approach to this perturbative expansion of Chern-Simons via this theory of quantum wave functions. And here we use, in essential way, both sides of holomorphic Floer theory, de Rham and Betti. Because on the de Rham side, we consider standard symplectic vector space, say this one, we quantize it using Mayal product. So what we get is a Weyl algebra, some non-commutative algebra. To each of these two complex Lagrangian submanifolds, one can assign modules over this algebra. And these modules are cyclic. They have cyclic generators, which we call quantum wave functions. And it turns out that holomorphic Floer theory gives a natural pairing between this quantum wave function, which is a formal series in general, formal series in H bar. And so in addition to this relation, there is a conjecture that this pairing of quantum wave function gives the same perturbative expansion. All right, so this is something not very precise, but now I'm trying in the remaining 15 minutes to be much more precise and more mathematical. So it's kind of the end of the introduction. And from now on, I will start to discuss finite dimensional exponential integrals and their relations to this geometry of two holomorphic Lagrangian manifolds, zero section, and the graph of the differential. All right, so this is a brief reminder. And in addition, I will assume that my affine variety is scalar. It's non-compact scalar manifold. So this is the notation for critical set, critical points, critical values. And the next thing I will need special generators in the homology groups, which are called symbols and which are described here, And let me explain what's going on the picture rather than to read the definition in words. I take the critical point of my function, xi, and I consider all gradient lines of the real part of f with respect to the Kähler metric. I can shoot this gradient line in any direction. So let me fix the angle theta and shoot the gradient line in the direction theta plus pi. So, which means that I consider the union of all gradient lines such they all are projected in the ray with angle theta plus pi, so this green ray. So such a union of gradient lines is a real Lagrangian submanifold. So if I have a Kähler manifold, it's also a real symplectic. So, and this is a real Lagrangian. It has a dimension 1/2. And so under some mild conditions, these Lagrangians, which are called symbols, generate the lattice of the relative homology, middle dimensional relative homology of my Kähler manifold X, relative with respect to the fiber of F at the point Z, which is very, very far. Let's call it infinity and use this notation for this relative homology, modulo torsion. Okay, so then what we have in the story is the lattice, is free abelian group gamma, the global relative homology. And this, there is a so-called local to global Betti isomorphism, which identify this global homology group with a direct sum of locals. So this is a picture. Again, it's easier to show it on the picture. For each critical point, I consider the tubular neighborhood of the critical fiber. And instead of shooting the symbol all the way to infinity, I shoot the symbol which ends on the boundary of this tubular neighborhood. So then I have the local homology, just exactly the same story, but infinity, if you like, it's specific to the chosen critical point or critical value. So this global gamma, global relative homology, is a direct sum of local relative homology group and the direct sum of all critical points. All right, how all this is related to exponential integral. So the thing is that if I have a basis in the relative homology, then any integration cycle is a linear, integer linear combination of this basis, which means that my integral is a linear combination of some basic integrals over the symbols. Let's introduce them. For each critical point or the critical value, let's consider the integral, this integral over the corresponding symbol. If my f is Morse, then there is a unique symbol. All right. So then it's enough to study the collection of these integrals, finitely many of them. And they are well defined as long as my exponent decreases along the integration cycle. And this is what I did. My choice is such that, yes, the integral is well defined. Now, maybe one remark, which may be useful, maybe not, that as any integral over the form over a cycle, it can be thought of as a pairing of something de Rham with something Betti, or it can be thought, if you like Hodge theory, it can be thought of as an isomorphism, which is the same as non-degenerate pairing, but people sometimes like to say that it's an isomorphism between de Rham and Betti cohomology. And this is what happens here, but at the level of exponential forms. So then what's going on here, it's a part, if you like, of exponential Hodge theory, and such an integral can be thought as an exponential period. There is such a theory which we developed with Maxim in one of our papers on cohomological whole algebras, which is very useful. But just it's instructive, but it's useful, but will not help us to study analytic properties of exponential integrals. Now comes the main thing, which is a wall-crossing formula. So when we cross the Stokes ray, and Stokes ray is a ray which contains at least two critical values, and we can assume that they are in generic position, which means that the Stokes ray contains exactly two critical values. And when we cross the Stokes ray, then the integral over the symbol I is changed, and it's changed by this amount. Nij is a certain integer number, and this is the integral symbol from the outcoming from the critical point xj with the critical value zj. So this is the simplest possible wall-crossing formula. This number can be interpreted in different ways. For example, this is exactly the number of gradient trajectories of this function joining the critical points. Maybe you remember generically these gradient trajectories are absent, but for some specific values which belong to Stokes rays, they appear. Okay, so then we have these wall-crossing formulas. Now let's modify a little bit the exponential integral and get rid of this factor and exponential factor as well. So these modified integrals admit, it's a corollary of the stationary phase approximation, they admit a perturbative expansion which has the Taylor series. For these modified integrals, we still have jumps when we cross Stokes rays. It's just a corollary of the previous formula. And what I would like to do next, I would like to construct a certain holomorphic bundle. So I would like, it's kind of to combine all the information just in one geometric piece of data. I consider the vector of these modified integrals, and I claim that this vector or its component, it satisfied a certain Riemann-Hilbert problem with jumps across the Stokes rays. And these are examples. These are, if you like, from this you can derive these Riemann-Hilbert problems. And so now if you have the Riemann-Hilbert problem, and in addition you have a section at each Stokes sector, in the sector bounded by two consecutive Stokes rays, then you can use the solution to this Riemann-Hilbert problem in order to do a holomorphic vector bundle. First, you glue it on C star with the coordinate h bar, but it turns out that it can be extended to C because if you look here, these factors has exponential decay along Stokes rays. So that we get in the end, what we get in the end, and is a holomorphic bundle on C star together with the section. And this is something quite general. This is something which appeared in a more general framework, which we developed with Maxim in the framework of analytic wall-crossing structures. Now, let's see. So I have like maybe 5 minutes or so, maybe a bit more, because I started a little bit later, left. I can axiomatically recall you what is the wall-crossing structure, or I can, no, probably let's try to do this. It will be instructive. What is the wall-crossing structure in general? The wall-crossing structure, it's something which we introduced for a completely different purpose, for the purpose of our theory of Donaldson-Thomas invariants, which actually I explained in my Tsinghua colloquium, I believe like 7 or 8 years ago. And the wall-crossing structure is a local system over some base. In my case, it's just C star. It's a local system of more basic objects, which we call stability data on the graded Lie algebras. So this structure, stability data, it's so general that this summer we will have a school at IHS. We organize it with Maxim, which is devoted specifically to stability data and wall-crossing structures. It's sort of ubiquitous. And probably it will appear in research of some of you. So what are the data for the stability? What are stability data? First, we have a free abelian group of finite rank, and in what we discussed today, it will be the relative homology group. In physics, it is known as a charge lattice. We should also have, and it's part of the problem, in physics it arises probably from the particular theory, we have a gamma graded Lie algebra over rationals, over complex numbers, anyway, over a field of characteristic 0. So then we speak about stability data on this graded Lie algebra. And these stability data are given just by indeed two pieces of data. The homomorphism of this charge lattice, which is known as central charge as physics. It's just in physics, it's homomorphism of abelian groups. And most important, it's a collection of elements, one element in each graded component. This is something which corresponds to the enumerative invariant, to a Donaldson-Thomas invariant. So these data are required to satisfy certain axiom, which basically says that the kernel of the central charge is separated from the support of this collection, which means that if A of gamma is non-zero, so Z of gamma cannot be equal to 0. And so having this data, one can construct a collection of groups, actually decomposing the plane into the union of sectors. One can assign to each sector, so this is a picture, decompose into the union of sectors. To each sector, one can assign a group, just exponent of the direct sum of graded components with a central charge belonging to this sector. And moreover, using this element, say, of gamma, one can associate elements of the groups. So this is what's going on. With each sector, which is less than 180 degrees, one can associate a group and an element in this group. And each element is a product over all rays, and there can be countably many of them. It's a question at the beginning of the talk, but this product taken clockwise is well defined. So this collection of elements is equivalent to the notion of stability data on the graded Lie algebra. And so there is a theorem, which is an analog of the well-known theorem from Bridgeland stability conditions, that on the set of all stability data on the given graded Lie algebra, there is a Hausdorff topology such that the projection of this space to the central charge is a local homeomorphism. So then the wall-crossing formulas, in particular those which I discussed today for the exponential integrals, is just a corollary of this theorem, although it's not obvious. Stokes automorphisms, which appeared several times in my talk, there's this AL in the general definition of stability data. And since maybe if you give me 2 more minutes, I will finish this slide. So just showing how the local system of stability data can appear in the nature. One consider an integrable system of Seiberg-Witten type. It's a complex integrable system such that the fibers carry meromorphic form, one forms with trivial residue. So then homology of these fibers, which are tori, they give a local system of lattices. The lattices are symplectic lattices, so there is the corresponding graded Lie algebras, toroidal Lie algebras, and the integral of this Seiberg-Witten form of the homology class is a central charge. The most interesting part is this collection of enumerative invariants, which conjecturally described in our paper with Maxim. All right, probably I should stop here. And you see there are like 43 slides, and this is, I'm not sure that this is even 1/2 of them. So I can just email you the rest, and you can post it along with the video. But I believe that I have convinced you that the wall-crossing structures are indeed relevant to exponential integrals. Okay, thank you very much.
Wow, thank you. Thank you for a beautiful talk. So I believe Professor Soibelman will be happy to answer some questions. Question, please.
Okay, there are some questions actually in the chat, which I did not answer because, yeah, I answered the first one. The number, doesn't have to be finite. Does the Stokes refer to Stokes Yes, the answer is yes. There is a full agreement with terminology in differential equations, which means Stokes matrices, which relate to fundamental solutions on two different sides of the Stokes race in differential equations. Yes, the terminology completely agree. So one of my point was to show you that there is a geometry behind of this terminology, and moreover, there is some algebra, these wall crossing structures behind the terminology.
Okay,
Right.
any more questions, please?
Hi,
Okay.
Yan. Hi.
Yes,
Oh,
right.
okay, Conan, yeah.
Hi, are you?
Ah.
So can I ask you a question? How is this theory that you developed with Maxim related to solution of the Floer equation?
Solution to Floer equation?
Yeah.
Yeah. Oh, yeah. That's a sort of that's a story. So let's see. Let me think how to do this. Let me jump in my slide. Let me explain it in the example. For that, you need to consider Landau. Okay, let's look at this example. A pair of complex Lagrangians in some symplectic manifold. It doesn't have to be a standard symplectic manifold, all right? So let's consider the space of paths, this phi, with the endpoints on these two Lagrangians. On this space of paths, there is a holomorphic one form, and you can, the holomorphic one form is given in terms of integrals. So, okay, so I can explain how it is defined, but there is a holomorphic one form, all right, which is closed. Then you can believe that there exists a potential, a function. It's everything is infinite dimensional. There is a holomorphic function, differential of which is equal to this one. Then you can try to construct, to work out the Landau-Ginzburg model for this potential on the infinite dimensional space. And when you try to do this, you will have to solve Floer equations.
Yeah.
So
yeah, are there explicit relation between the number of those solutions and the wall crossing formula?
Yes. When I'm not sure. I'm not sure how far people. I heard a couple of talks on these attempts use Floer equation for constructing Landau. I mean, in the end, yes. In the end, it will be just wall crossing formulas for this infinite dimensional Landau-Ginzburg model.
Yeah.
In the end, but I don't think that it's mathematically sound this time. Yeah, there are some names probably you know better. Don, Reshikov, Pierre Bousseau started to be interested, but I think it's kind of analytic difficulties are very big. And
also, the work are mostly just for nearby Lagrangians, what they do, right?
What?
I think the work is mostly for nearby Lagrangians. I mean, L1
Oh yes. You see, what we are trying to do with Maxim, it's not clear. I mean, it's difficult to explain in a short. We try to avoid hard analysis. You see, and these infinite dimensional manifolds. What we suggest are finite dimensional constructions, which conjecturally give the same answers. These infinite dimensional considerations. Yeah, so what I believe that kind of probably we will be able to propose a wall crossing structure for this Landau-Ginzburg model, without, so someone, I don't know, will define rigorously what are these numbers. This is true, but this wall crossing structure, we can probably will be able to describe it without taking these numbers as a black box. Yeah, so at least in 3 dimension, in the case of Chern-Simons theory, this is part of the slides, which I will be happy to email, whoever like them. In the case of Chern-Simons, yes, we have a conjectural wall crossing structure, which is essentially given in finite dimensional terms. And it answers many questions in the Chern-Simons theory. For example, resurgence of the perturbative expansions of this Chern-Simons partition function.
I see. Another question is, you're thinking about if you have this holomorphic Morse function, right, you view it as 2 Lagrangian inside the potential bundle of C. Right? C is the parameter H bar. Can you view this on the 3D mirror side? This wall
You see, I understand what you mean, but the thing is that it's not about mirror symmetry, I would say.
3D.
You mean 3D? About 3D, yeah. I think I can, at least in examples. You see, there is one structure missing. I mean, it's deliberately missing in our theory with Maxim. We do not have a C-star action. So if you look at this 3D n equal 4 Coulomb branches story, the life begins, at least it's my understanding, maybe I'm totally wrong, when they have a C-star action.
But this side you don't, because this side is
yes. In this example, yes, I agree.
Yeah.
Yes, in this example, yes. In this example, yes, we do. But the key part of our story is a Riemann-Hilbert correspondence, which is not a part of mirror symmetry.
Yeah.
It indeed relates some holomorphic objects to some symplectic objects, but they stay on the same side.
Same side,
Yeah. So probably I would say that our geometry, it's rather this parameter h bar, which appeared as a Planck constant in my talk, it should be rather thought as a twistor parameter. So we should think that its h bar belongs to some twistor CP1, and we have a family of theories parameterized by this. So then, since it's, well, let's call them hyperkähler, although it can be not necessarily hyperkähler, but only complex symplectic, then yes, indeed, we can try to think of all what we are doing as sort of Coulomb branch type business. Yeah, we have not thought about it because even this, this exponential integral story, which we are trying to finish now, it's like more than 100 pages paper. And altogether, it's more than 400 pages file. So it's a lot of stuff even without C-star action. But what I would say, how one can use holomorphic Floer theory, in conventional Floer theory, or rather Fukaya category, there is a notion of Lagrangian skeleton. And it's very useful if you have this Liouville field action, which contracts everything to this Lagrangian skeleton. It's a sort of a singular Lagrangian which generates your Fukaya category. Now, in this holomorphic Floer theory side, there should be a holomorphic Lagrangian skeleton, which is a singular holomorphic Lagrangian manifold. And everything, including the mirror dual, probably can be spelled out in terms of this. Yeah.
So this symbol that you describe in your talk is like the custodial of that skeleton. Right?
Say it again.
Those symbols that you discussed in your talk, in a way, it's a custodial to the skeleton. Okay.
Yes, but the thing is, you see, the symbol is a real Lagrangian in the well, in my, at least in my talk, it was a real Lagrangian, not the complex one, in the Keller, in the symplectic manifold, which is a Keller manifold. I understood your question as a question about holomorphic story, which means that I take this Keller manifold, which is a complex manifold, I take a tangent bundle to it. Now it's a holomorphic symplectic. And then I don't know what to do with symbols. You see, symbols for me, they were just certain bases in the whatever homology groups I consider. If you'd like, symbols correspond to intersection points of two complex Lagrangians, if you'd like. So in the Floer or in the Morse theory, you have not only the homology group, but you have a basis, because these critical points or intersection points in the Floer theory of two Lagrange gives you a basis. So that these symbols is just a basis. For example, if your function is not Morse, you do not have symbols. And you should consider, and it's on the slides, which I will email. So you consider the cohomology with coefficients in the sheaf of vanishing cycles of your function. So there is no distinguished basis. So this symbol story, it's rather misleading. But the general formalism, which I was trying to explain, it can be upgraded to not necessarily Morse functions story. You have two Lagrangians, for example, which intersect not necessarily transversally, and still there is a wall-crossing structure, everything works. In particular, you can consider in Chern-Simons theory non-isolated connections, which it's far beyond what Witten was able to do in his paper about analytic continuation of Chern-Simons. So this theory is more powerful than the example which I
how about if the critical point, instead of being isolated, but itself is holomorphic symplectic? And any good example? Because in that case, the symbol may be coisotropic A-brane. Maybe you can use that as a morphism space to form.
Okay, the thing is that if the intersection is not clean, I don't care whether something is coisotropic, isotropic, it's just a closed subset. The point is that with intersection locus, like this L0 intersected with L1, like on the slide, I can associate certain perverse sheaf.
I'm not saying the intersection. If you look at the intersection point and flow it.
Yes.
And then the whole thing becomes coisotropic A-brane.
Yeah, you can go very far. First of all, these Lagrangians, as well as a simple, you should understand and put it the right thing as in DG sense. You have a DG symplectic stack. And you have an intersection of two Lagrangians in the sense of these shifted symplectic structures. So by theory, I believe by Joyce and others, you have this perverse shift and so on, so on. Yes, indeed. Yeah, I agree that in the holomorphic setting, yeah, that's actually what I'm trying to say. But the point is that there is something, there is this wall crossing structure which controls whatever, everything, like, for example, perturbative expansions of this infinite dimensional integral, so, or enumerative invariants, like what you mentioned, this for further solutions to further equations. So there is some formalism, so that's the point.
Okay, any more questions from the audience? Okay, so everybody.
Well, it's great, Yang. So this is Yao. So will you be interested to come in January to visit us? Maxim is coming for 3 weeks.
Yeah, but that's what I mailed today.